Okay, so let's start this afternoon session. So we are very happy to have Yariv Kafri from Technion here, and thank you, Yariv, to actually agreeing to give these talks online. So yeah, so I guess it will have. So let's see how it goes, and if people have any question, I think you don't ask immediately. Wait for the speaker to pause, or maybe you can raise your hand in that raise button, and then you can ask the question sometimes later. Yeah, Yariv, to you.
Okay, thank you very much for the invitation. As you might have heard me say, I don't have much experience with teaching on Zoom, so I hope it goes smoothly. So what I'm going to talk about, the statistical physics of rare events, and specifically large deviations, will be the focus of the talk. And I'm going to start the lecture as in a sort of funny way. So the outline of the talks will be roughly as follows. I'm going to start with not giving any motivation or anything like that, but just looking at the mathematical question. So I'll define what we mean by a large deviation, even before telling you why it's of any interest. And I'll add to this a small calculational trick, which is so useful in the field that I want to show it, but nonetheless, I'm not going to use it in the talks that I'm going to cover here. Then after I define what large deviations are, I'm going to give you motivations for studying it. And those will come both from inside and outside physics. And I'm going to sketch through them and end with specifically something that's been of interest for a while now, for almost 20 years, which is large deviations in macroscopic systems. And that will lead me to consider the limit of weak or small noise. And what I'm going to do is I'm going to teach you, by using trivial examples, how one calculates large deviation functions for systems with small noise. And this will break into two parts, which are both used very, very, very commonly in the literature. The first is a Lagrangian approach. And the second is, as you might guess, Hamiltonian approach. And I'm going to guide you through these things. And the Hamiltonian formalism will allow us to specifically derive many general properties that I'm going to discuss. Throughout, I'm going to emphasize the difference between systems with detailed balance versus systems without. So if we get through this part of the talk, and I hope to do more than this, then at least when you open a paper which calculates a large deviation, and to a large extent I think about it at this stage as a calculational tool and not necessarily as a research subject on its own, you'll be able to pick up a paper and understand the calculations done, even if they're done on more complicated systems. And if I achieve that, then I'm very happy with what I've done. I've taught you something useful. But if I have time, I'm going to discuss some recent results. I'll start with something that's already more than 10 years old, which is large deviations in diffusive systems. And if I have time, I'll discuss some more recent results on large deviations in the context of active particles. And depending on time, I might switch and decide which one I focus on. Okay, so again, the goal of my lecture notes is to teach you how to read and calculate yourself large deviations, and less so on bringing you up to speed on all the recent results. If you really want that, I might modify the last lecture. Okay, so given that I haven't really done anything yet, I'm going to jump into the mathematical question. And again, I'm going to try and do this throughout the talks here. I'm going to use the simplest problems that we can imagine applying these tools to. So I'm going to consider n coin tosses. Sorry. So n coin tosses. And I'm going to imagine that the outcome of the coin toss is either 0 and 1. And my interest will be in calculating the probability of a random variable taking a value a, and where the random variable is defined by 1 over n, sum over I equals 1 to n of Si, where Si takes the value 0 or 1. What I want to stress from the start is that A is intensive. Okay, it doesn't scale with the number of coin tosses in the system. Now this is a trivial problem which everybody knows how to solve, and you might tackle it by a host of methods. The first thing that might come to your mind is the central limit theorem. And what we have to do is we have to calculate the first cumulant of the random variable S. We have to calculate the second cumulant of the random variable S, which is 1/2 minus 1/4, which is equal to 1/4. And if we do this, the central limit theorem, I'm going to be a bit formal here, tells you that if I look at the limit of n goes to infinity of observing the probability of a variable y given by NA minus n times the first cumulant divided by square root of n, then in the limit of n goes to infinity, this behaves like a Gaussian. Okay, so this is all very basic at the moment. And again, the statement is that when n goes to infinity, and we look at this rescaled variable, then we observe a Gaussian. Now, what I want to stress is that when the variable NA minus n times the first cumulant, namely the deviation from the mean, does not scale like square root of n, then the central limit theorem predicts a 0 probability. Okay, so any deviation that doesn't scale like square root, or in the language of the variable a that I've defined, a minus square root of s goes like 1 over square root of n. Anything that's a larger deviation by that, by default, by the central limit theorem, is exactly 0. There's no probability of observing such events. Questions so far? Okay. Everything's A-okay, and you've seen this before, I'm sure. Okay, another thing we can do, we can solve this exactly. So we can solve the problem exactly. And that's easy enough. The probability of A equals A is equal to 1 over 2n n factorial divided by na factorial divided by n times 1 minus a factorial. So that's easy enough, and you can plot how this result looks. Of course, if we look at deviations where the variable a minus the average is larger than 1 over square root of n, specifically when it's of order 1, then this quantity is not 0. So this has more information, as you might expect, than the central limit theorem. Now, what I want to do is I want to massage this object. So what I'm going to do is I'm going to use Stirling's formula. So n factorial, I shouldn't write them equal, asymptotically behaves as n to the n e to the minus n square root of 2 pi n. And if I use this, and I'm going to skip a bit of math, I can find that the probability of the random variable taking the value a is given by 1 over square root of 2 pi, square root of n, square root of a times 1 minus a, and then e to the minus n times log 2 plus a log a plus 1 minus a log 1 minus a. And if you've done enough statistical mechanics, then you recognize this object for many, many problems. For example, just a hardcore gas. And what I want to stress is that this accounts for values of the, this dependence accounts for deviations which don't scale, where a doesn't scale like 1 over square root of n, but a can take any value up to 1. Now I'm going to write this in a slightly different way. I'm going to write this as e to the minus n I of a plus corrections which are order small o of n. So I should write this nicer. So this is small o of n. Okay, so this small o of n accounts for all these guys, which in this case are logarithmic corrections. And here I've defined I of a is equal to log 2 plus a log a plus 1 minus a log 1 minus a. Okay, so this guy describes deviations which are of a, which are of any order where a is any value of a if you want. So in the large n limit, clearly the probability of observing a equals a is captured given to leading order by p of a equals a goes like asymptotically like e to the minus n times I of a. Okay, so I should actually move this and mark it, because this will appear in many, many places. Sorry, I'm going to have to get used to this thing. Okay, so this is the asymptotic behavior of the probability of observing the variable taking the value a. And we call I of a rate function or a large deviation function. Okay, so that's the definition of the large deviation function. Any questions at this point?
Hi, sir.
None?
Hi, sir.
Yeah, I think there's a question.
Okay.
For central limit theorem, if the fluctuations are really greater than, let's say, root n, I mean, is there any comment from central limit theorem that it has to be 0? Why did you say it has to be 0?
Well, if you look at the strict form, if you open a mathematician's textbook, the central limit theorem is given by this expression.
True.
Okay, so it accounts only for deviations of the variable a from the mean value, which scale is 1 over square root of n. Anything that scales in a different way, its probability within the central limit theorem is strictly 0. And that's not the case here.
So central limit theorem has that statement that the probability has to be 0 for deviations from the mean, large deviations from the mean.
So within the central limit theorem, you're not, it's a different, I like to think of it as a different scaling regime. You're not looking at, you're looking at deviations which are very, very small. You're looking next to the peak of the probability distribution. And this guy is really looking, sorry, I'm pointing to myself. This guy is really looking at the tail of the probability distribution.
Okay, thanks.
Okay. Yariv, I have a question.
Yeah.
Yeah. See this formula that P of A you have written, that approximate formula, which has this 1 by square root of A into 1 minus A and then exponential of n times this function, right?
Yeah.
Yeah. So I guess this is not strictly valid when A goes to 0 or 1, but one can probably say till when it valid, what is the some 1 minus some n dependent, 1 by n dependence term, right? Because the large division function is still valid, I mean, still a well-defined A equal to 0 and 1, but you have this divergence.
Right, right.
Yeah.
So
I guess one can,
boundaries of the term, then you have to be a bit more careful. Yes.
Yeah. So I guess one can say that it's like valid till 1 minus some n dependence term, which goes to 0 as n goes to infinity.
Yes, yes, yes. Thank you. Okay. Any other questions? Okay, so I want to make some comments about this. So the first one is just to stress, n is extensive. This will come in on test later, while in A is intensive. Okay, we build the variable A, so it's intensive. If you look at a formal definition of, sorry, there was a question?
I think there's a question in the chat box. It says, is it possible to look into deviation of order, say, n to the power minus 2/3 in this problem from Arga?
So A accounts for deviation. So in the large deviation form, we're interested in deviations, deviations. If you look at it simply, you're interested in A, which is finite, but I'm going to tell you how you can get something like you're asking in a second, okay? From the result that we have. So let me get back to what I was, so if I don't answer that in a second, bug me again. So formally, if you look at a textbook on how a large deviation function is defined, then it's defined as the limit of n goes to infinity of 1 over n of the limit of p of A equals A. So in principle, if you have an exact solution for the probability distribution, all you want to do is you divide it by 1 over n, and you send n to infinity, and you can convince yourself that that's exactly what we have in our simple problem. The next comment is that I of A describes fluctuations, sort of going back to the questions, fluctuations much beyond the central limit theorem. Okay, and finally, and I hope this answers the question that was raised a second ago, that if we look close to the average value of 1/2 in our problem, we can expand A equals 1 minus epsilon to the leading order contribution in epsilon. And I'm going to skip the line of math that does that, but what you find out that you have 2 minus 1/2 squared, which agrees with the central limit theorem. So specifically, just to answer the previous question, I'll be a bit more careful. Taking a scaling form of epsilon equals A over square root of n, and then taking n to infinity brings back the central limit theorem. Okay, so I hope that answers the question. Okay, and the purpose of this talk is to sort of bring you up to speed on how you can calculate the rate function, specifically in the context of physics problems. Now, before I jump into the motivation, there's a standard trick for calculating, so I'll call it a trick, but there's probably a better title for this section. There's a standard method for calculating large deviation functions, which avoids going through the exact solution. Okay, and what I'll try to convince you is that StatMech is doing that all the time. So I'm going to remind you of something that we do in equilibrium, and then I'll just translate this method exactly to the problem that we just described. And again, the problem that we did is so simple that you can solve it whichever way you want, but I'll show you that there's a simple way that for more complicated problems is very useful. So, so what I want to do is think about equilibrium problems. So you're doing some statistical physics of an equilibrium problem, and you want to calculate the entropy. Now you know that, generally this is a very, very, very hard problem. Even, I'll try to venture, even for an ideal gas, it's not a very hard problem, but it's not a completely trivial, okay, it's trivial, I'm pushing the limits here, but generally calculating the entropy can be a hard problem. So what we do typically is we change ensembles and we go into, so to simplify, many times we go to the canonical ensemble. So what we do is we just define a partition function, which is sum over omega of E times e to the minus beta of E. And this is the density of states. So log of this up to a Boltzmann constant is the entropy. So density of states. sorry, states. Okay, and what we do, you know, even for, again, going back to the ideal gas, this calculation is a one-line calculation. And then what we do is we use the fact that because this partition function is a sum of terms which are exponential in the number of degrees of freedom in the system, then we can estimate this whole sum just by carrying out a saddle point calculation. So we know from statistical physics that this whole sum is dominated by one term, which corresponds to a specific value of the entropy. And I'm just going to massage this term into a different form. So minus 1 over beta log omega of epsilon star, which we also know as e to the minus beta f of epsilon star, where epsilon star is a solution of beta equals t log omega t epsilon. Now I want to stress that, as you probably know from StatMech, you never actually have to do this calculation when you're doing StatMech. Okay, so what we do is we calculate the partition function, which releasing, because we've released the constraint over epsilon, is a much easier problem. And we know that this guy is dominated by the saddle point, so the partition function is equal by e to the minus beta f of epsilon. And with this, we can evaluate the entropy, can obtain the entropy from f of epsilon star. So what I mean by that is, first, calculate the energy as a function of beta, the inverse temperature. So you get a relation between beta and epsilon star. And this you do by using E of beta equals minus d log z d beta. Okay, just standard StatMech. And when we have that, then we can use the relation that the entropy at energy E star is equal to E star minus the free energy at E star times beta. Okay, so that's a simple way of obtaining the entropy by releasing a constraint on the problem that we're dealing with. Okay, so this is standard StatMech, and again, the basic idea is that we have this function omega of E, which is growing very, very fast with epsilon, and you can think about it as a mathematical trick. You multiply this function by an exponentially decaying function, you get a sharply peaked function at some value epsilon star, and then you move this function with beta to select different values of epsilon star. And this is a completely standard trick also in probability theory. For example, if I'm not mistaken, a Chernoff bound, you replace the exponential function by a step function, and there's all sorts of variants of this very same idea. Okay, so far, questions? So questions, there was a question on numerics. I'm not going to discuss numerics, but other questions.
So, hello.
Yeah.
Yeah, I have one question regarding the saddle point approximation for the equilibrium case you did.
Yeah.
So when we are doing the saddle point approximation, we are implicitly assuming that E and log omega scales in the same way, right?
Yes. Right. That's the...
Why is it so? Like Is
Well,
there any
typically we assume
justification?
that the energy is additive, right? If it's not additive, then things become different in StatMech, but the entropy is additive, so it scales. So to make it quantitatively, if we have n degrees of freedom, then we expect the energy of the system to scale like n times the energy of a box, a small box inside the system. And similarly, just from combinatoric arguments, you could argue just by think about coin tosses that n will generically grow exponentially with n. Omega will generically grow exponentially with n. Okay, now there are cases.
Log omega has to scale with n.
So that means, so because log omega scales like n times some some other function, okay, specifically you could think about the energy divided by the number of degrees of freedom. So that means that omega grows exponentially with n.
But if we have interaction among the particles, then energy may not scale as NE, right?
Now, if you have short range interactions, think of two boxes with energy E1 and E2. Let me close the window. Okay, sorry. So if you have two boxes with energy E1 and E2, and you put the two boxes together, then if the interactions are short range, then the total energy is E1 plus E2. There are some small corrections which come from the interactions along the boundary. But if we think of a three-dimensional system, then E1 scales as the volume, and this interface grows as the volume to the 2/3. So it's a subdominant contribution. Okay?
Okay, thank you.
So if you have a gravitational system, then this breaks down, and you have to be more careful with what you do.
Okay, thank you.
Okay, any other questions? Okay, so just to recap, calculating omega is hard, so we calculate what we call a partition function, okay? And then this is an easier calculation. I'm not saying that it's easier, but it's an easier calculation. And once you have the partition function, you can extract the entropy directly from the free energy. There's other methods by differentiating the free energy, but it doesn't matter. The point is that you don't have to calculate omega directly. You can calculate it by this shortcut, easy trick, an easier way of doing the calculation. So what I want to do is now use same idea for a coin problem. Okay, so in case you saw that, I apologize. So the analog of, so if you look at this guy, so I should ask a question and get an answer just to see some feedback. What sort of quantity does it remind you in probability theory? Anybody answer? Okay, no one? Okay, so this reminds you of a generating function. Okay, so a direct analog of a partition function up to a normalization is a generating function. So I'm looking at the average of e to the nka. Okay, so the analog of beta from the previous calculation is k here, and na is the analog of the energy in the previous calculation. And this guy is something that we use in probability theory a lot, because once we have this guy, we can differentiate it and obtain, for example, different moments, or if you differentiate the log of this guy, then you can obtain different cumulants, etc., etc., etc. Okay, so I just want to rewrite this in a funny way, which sort of reminds you of StatMech. So it's e to the log of e to the nka. So I've just exponentiated this guy. And then by definition, this is equal to the sum over all values of A of the probability of observing A times e to the nk A. Okay? Now, the probability is exponentially small. This generating function scales exponentially with n. So we can again apply a saddle point argument, and this will be dominated by a specific value of A, which we obtain by solving the saddle point equation. So this is saddle point calculation. Okay, so this, we get this value of A star by analogy to the equilibrium case, we get by solving the problem n times k plus the derivative of A divided by n p of A equal to 0. Okay, just by doing the saddle point on this object, by just so I'm completely clear, I write this as e to the log p of A and take an n outside, and I just do a standard saddle point calculation. Okay, so if we have that, then I can write this guy. Again, I'm just massaging it. It all should be familiar if I've done a decent job to the equilibrium case. So I rewrite this as e to the nka plus log p of A star. So all I've done here is just exponentiated this guy. So if I'm interested in calculating the probability of P of A, which might be a very hard problem, then what I do is I introduce a generating function, which if you've ever played with it is a much easier problem than calculating P of A directly. Typically is an easier problem. And then because we're looking at things that scale extensively in the probability, something that decays exponentially, this whole sum of the generating function is really dominated by one term, which is the exact analog of the partition function being dominated by a single term in the sum. So let's use this now to calculate. So you can see that, just to be clear, we now have a simple relation between the generating function and log of the probability of observing A. And what I'm going to do is I'm going to sketch how you do this derivation to obtain the large deviation function in the simple coin toss problem. So the first thing that you do, again, like equilibrium, we want to calculate. So what we're going to do is we're going to look at coin toss problem. Okay, and the idea is that if we calculate e to the I nka, okay, so here it's a really simple calculation. So we do e to the k sum over 1 to the n of si. Okay, just a second. Si, and I'm going to leave it as a small exercise. If you really want, I'll do it, but I think many of you can probably do it in your head. And you find out that this is the expression for the generating function. Just the probability of observing si equal 0 is 1/2. The probability of observing si equals 1, which gives you an e to the k in the generating function, is 1/2, and we have independent variables, so we end up with this simple expression. So now we just use the trick from StatMech. We calculate A as a function of K. How do we do that? Well, we just differentiate the generating function. Okay, so this is standard generating function tricks. You can convince yourself that this indeed, the derivative with respect to the exponential pulls down A, and the log just takes care of the normalization, and you get e to the k divided by 1 plus e to the k, which you can solve, and again, it's a one line of math, and you can express k as log a divided by 1 minus a, or e to the k is equal to a divided by 1 minus a. Any questions so far? Nothing. Okay, if I'm running too fast, now is a good time to stop me. So now that we've found the relation between A and K, okay, which is directly the analog of the relation between temperature and energy, then we can use log P of A star is equal to log of the generating function minus nk A star. So just to remind you, we had this simple relation between the generating function and the probability, the log of the probability of observing a variable A. So what I did is I just solved for log P of A star, and I get log of the generating function, which is like the free energy in equilibrium, minus nk A star, which is like the average energy, the energy in equilibrium. So now all we have to do is use the relation between K and A and plug it back in. And what you get is that log P of A, and I'm dropping the star because it's not needed anymore, is equal to minus n, I'll do it in one step, plus n log of 1 plus e to the k, minus na log of a divided by 1 minus a. So this guy is just k. And what I'm going to do is I'm going to replace e to the k here with this expression. And once you plug that in, you get minus n times log 2 plus 1 minus a times log 1 minus a plus a log a, which is, as I've argued before, the rate function for this problem. Okay, so in a sense, and that will be some motivation for what follows, what we do in StatMech all the time is deal with rate functions. Okay, questions? Okay, so I don't know, am I talking to myself? It's a good time to let me know.
So, can I ask one question?
Sure.
In the equilibrium case, that when we discuss the saddle point for the equilibrium problem, it turns out that E star is also the average energy, right?
It's the average energy, but remember you fix beta, and for a given value of beta, you get the specific energy.
Yeah, I was wondering, so even in the coin problem, is A star the average, like average value of that?
So let me repeat. I wasn't very clear. I apologize. Suppose that you want to calculate omega as a function of E. So you give me the energy, and I tell you the entropy at that energy. Okay? So that's the question that I'm asking. So one way to think about that is, forget the physics textbook, get a math textbook. And what a math textbook will tell you, well, if calculating omega of epsilon is hard, what you do is you multiply it, you sum over all energies, and you multiply it by a decaying function. This is the exact analog of a generating function. So if I look at this figure, omega of epsilon is a strongly increasing function as a function of energy. And then I multiply it by e to the minus beta e, which can sit here, or if I take a different value of beta, it will sit here, or here, or here. And by selecting the value of beta, I can isolate different points where epsilon star is the average of the average value. Okay, so by changing beta, I'm sort of poking this function at different points along the function. Okay, and if I've done that, and I find the relation between which value of beta pokes which value of epsilon, then I can find the entropy at the specific value of epsilon. Okay, so really we're interested in S as a function of epsilon. So in StatMech, what I'll do is I'll take this beta and write it as a function of epsilon. And I'll take the free energy, which is typically, we like to write it as a function of the temperature or the inverse temperature, but here I'll express it in terms of the energy, and that's it. I have the entropy. I don't have to calculate in the microcanonical ensemble. Now what I've done here is the exact same analog. I multiply it, keeping k completely arbitrary. Okay, so different values of k would correspond through this solution, right? Or this solution, or this solution to different choices of A. And by using this relation, I was able to obtain the probability, which is the analog of the entropy, for any value of A. Just by expressing it instead of in terms of K, as a function of A. Okay, does that clarify things?
So, but I'm confused, like, what is this AK here below the generating function?
Right, so again, let's think about it, let's think about this in a pictorial way, okay? So I'm taking something that's a probability distribution, and let me look away from 1/2, okay? So it's a probability distribution that has some form that's decaying away from 1/2, okay? So now I'm multiplying, when I calculate the generating function, I multiply it by something that's increasing exponentially with k. So this will be one value of k, a different value of k would look like, sorry, I'm drawing it back, it should start here. Different value of here will, this will be a different value of k, etc., etc., etc. And each of these values of k will select a different value. I think I know what's calculated. So typically, I think I know what's confusing you. Sorry, I should have said it before. When you calculate, typically using a generating function, you put k to be 0. Okay, and here we're not doing that. Okay, does that clarify things? So for this value of k, the generating function will be peaked here. At a different value of k, the generating function will be peaked here. And this relation here tells me for which value of k, for every value of k, where the generating function will be peaked. Does that clarify things?
This AK is cumulant generating function, is it?
This AK is not, well, the AK is the relation, right, between the average value of A for a given value of K. Okay, it's the average.
Okay.
Okay, this is a relation. This is a relation between A of K, and I don't want you to think that's, I think that's where I got you confused. When you do a cumulant generating function, you differentiate and you set K to be equal to 0. Here, I don't want you to do it.
Okay, okay.
Okay, so you fix A, and then this function is peaked at this specific value of K. Okay, did that clarify things?
Yeah.
There's a question. What
yeah,
is
maybe
A?
there's a question in the chat which is related to what is, the question is what is A star in coin toss problem? I think the same.
Okay, sorry. So this is my lousy notation, sorry. So really what I should have here, that there's an A star, which is for every value of K, I select a specific value of A star. So this is this is A star of K1 here, and here it's A star of K2, etc., etc., etc. Okay, so you give me a value of K, and I tell you at which A star this function is peaked. Okay, and by tuning the value of K, I can move the position of the saddle point, and by moving the position of the saddle point, I can probe different values of P of A. Okay, so I think I've made I made it more confusing than it is, so maybe you should ask again questions.
I think now it's clear to me. Thank you.
Okay. Anybody else? Okay, so again, it's just a trick of calculating the probability distribution using a generating function. And as you can see, it's something that's completely analog to what we do in equilibrium all the time. And indeed, you can think about changing ensembles as it's a completely mathematical trick. You don't have to think of any physical connection to a bath necessarily. And many times it's useful to go into non-physical ensembles to do calculations. Okay, so this is something that appears in much of the large deviation literature, this trick, and using it exactly in the same way. But I want to focus on a different set of methods. But I sort of think that it's sort of a fun homework to do if you're motivated, and I'm sure you are. You could take an equilibrium problem and ask for something that you don't typically ask. So take a black body, which is a standard problem in StatMech. And you know that for a black body, the number of photons is not a good thermodynamic variable in the sense that it's not something that we can control externally. It's controlled by the minimization of the free energy. But nonetheless, you can ask, what's the probability of observing in photons in the problem? Photons in the system. Okay, so there's some average value of photons, which you can calculate using standard StatMech, but you could ask yourself this very, very silly question: what's the full probability of observing in photons in a black body? And for that, you have to introduce a generating function. I'll give you a hint. So I have to introduce generating function which is related to the number of photons. Okay, so I'll give you even more of a hint, and I'm going to mark it in a form that you might recognize. So, so the generating function in the notation of my coin toss, this would be my K. So the generating function, I wrote it in this way just to let you realize that by looking at this generating function, then the extra intensive variable that you introduce is very similar to a chemical potential. And then if you work this out carefully, you should find out that in 3 dimensions, if you look at the probability to observe a large number of photons in the systems, then there's actually a condensation of many, many photons in the lowest energy state in the system, because essentially what you're doing is going into a grand canonical ensemble with a chemical potential for bosons. Okay, so question about this homework? Okay, so again, the trick is that you're probing something that you wouldn't necessarily probe with standard stat mech. You're typically not interested in the probability of observing n photons in the system, but you might as well be interested in it and do the calculation. Okay, good. Any questions about what a large deviation function is, what a rate function is, etc.? Okay. You have to be more noisy because at some point I'm feeling like I'm talking to myself, which is, I guess, a prerequisite to being a physicist, but I don't want to push the limit. Questions? Okay. So with this in mind, I want to motivate why at all you're interested in looking at large deviation functions.
Sir?
Yes.
For a given temperature, I mean, the entropy will still be, I mean, if you want to find entropy, it will still be, have a distribution, right?
No, the entropy is a well-defined function of the energy.
But for example, a bath, I mean, for a system in equilibrium, temperature is, let's say, T, then it can have multiple energies, right? And so S of E itself is, S is a function of E, right?
Right.
I mean, S is a microcanonical thing.
So if you couple to a bath, and that's the magic of stat mech, if you take a system and couple it to a bath, then what you find out that the distribution of energies is very, very sharply peaked. In fact, if you look at the intensive energy, which is the total energy divided by the number, the fluctuations in this intensive energy go as 1 over square root of n.
Yeah.
Okay, so that means that the average energy is a completely well-defined quantity. You might as well, if you really insisted, integrate over all these states which are around the average energy, and you'll find out that they give you a sub-dominant contribution. And in fact, if you look at different textbooks in stat energy, but some window, a small window that's not extensive, and as long as it's not extensive, it doesn't make any difference to the thermodynamics of the problem. The entropy is completely unchanged. In fact, in quantum mechanics, this is essential because chaotic systems typically have very low degeneracy, and you have to look at some small window. Okay, so really there's a complete freedom of doing thermodynamics in any to get, sorry, let me repeat this. You get the exact same thermodynamics for any ensemble calculation that you do. It's just a matter of changing variables in a smart way.
But for example, if you want to find an arbitrary value for a specific temperature, can we actually find what will be the entropy for, let's say, okay, I'll frame it in a different way. For a system in thermal equilibrium, let's say at temperature T, we have the probability of the system having energy E as E to the power minus beta E. Similarly, can we have something like that for entropy? Instead of energy, we consider entropy.
Well, no, because if you look at, so again, if you look at many body problems, which are what we're interested in StatMech, then the probability distributions are very peaked at the specific value of the average energy.
I agree. But still, I mean, it's still a valid question, right?
You might have some, I don't know, maybe Abhishek and Sanjib know, I don't know. In standard systems, you might have some very esoteric systems where I guess, there's systems with long-range interactions, for example, where you have to be careful with different ensembles in different temperatures. But even there, I think that things are pretty well defined. I'm not aware of a macroscopic system with a very broad distribution of entropies. Maybe someone from the audience knows one.
Yeah, I can't think of example.
Okay, so again, the magic of StatMech is that you can do the calculation, and if you ever try doing an ideal gas of bosons or fermions in the microcanonical ensemble, it's a nightmare. It's not a simple calculation. In the grand canonical ensemble, it's a pretty simple calculation, and the results nonetheless apply to a system coupled to bath exchanging particles, isolated, whatever system you choose. That you could choose whatever ensemble you want. And again, I'm going back to what I said initially. You could think about it as a purely mathematical trick. You really don't have to think about coupling to a bath or anything like that. It's just a trick of singling out this specific value of the energy.
Okay.
A mathematical trick. And it's a completely legitimate way of doing the calculations for macroscopic systems.
Okay.
Okay.
Yeah.
Any other questions? Okay, so what I want to, yes.
Yep, I have one question, Yariv. So if we allow the coins to be correlated to each other, what is the degree of correlation this large deviation vessel can tolerate?
So you want something that decays fast enough so it will look extensive.
So in the end, it has to be effectively, should be able to be treated as independent variables.
You want to do all these tricks, you have to apply a saddle point calculation, and therefore it has to, the probability has to decay exponentially with n.
Thank you.
Okay. Otherwise, some modification of this might work. Anyway, there's been some recent work by Mailson on cases where the scale. Anyway, I'm jumping ahead of myself. Maybe at the end I'll discuss it. Okay, so I want to motivate why you would be interested at all in looking at large deviation functions. So I'm going to start with problems outside physics. And that's actually, to best of my understanding, this is where much of the field was originally developed. And the first thing you might think is risk management. And again, I'm not going to spend much time of it, but imagine that you have an insurance company and you know that your income is constant. Everybody's paying you such and such amount of money per year to insure their house. And you're interested in the probability of a rare event of some fluctuation which will bankrupt you. So you want to estimate what's the probability that you go out of business. It might be a very tiny probability, but if it happens, it's not very good. So I guess like COVID-19, that was an unexpected event, and that bankrupt many people. And you might ask, what's the probability of something like that happening? So this is the probability to go bust. Another thing that's of a lot of interest, also within the physics community, and probably in the next few years even more so, is population dynamics. Okay, so you're interested in, and again, there's a classic problem that people worked on, which is the Lotka-Volterra system, which again, I'm not going to discuss the details because we don't have too much time in these lecture notes. But you could ask the probability that if you have some population of, say, COVID-19, you might make a model for the dynamics of COVID-19 and ask the probability to go extinct. Okay, so you might want to do the calculation of what's the probability of something to go extinct. I don't know, I could imagine that if you're doing modeling of COVID-19, then you look at different models and you modulate different responses to the epidemic, and you might want to somehow maximize the probability that the virus goes extinct. And there's been a lot of work even by physicists on these problems. The other sort of problems that people have been looking at, I'll give one final example from outside physics. There's climate problems. And there's actually a beautiful work, there's a beautiful work that what people do is ask, what's the probability of a large fluctuation in the temperature so that things become dangerous. And one of the impressive things that people have been able to do using techniques of large deviations like the one that I'll describe now is actually show and check it against real experimental data, show that when you have a heat wave, which places become the most hot. So you can actually, using the techniques that I'll show, argue that if there is a large rare heat wave, then it's going to look in a very, very specific way. So climate problems have attracted also a lot of a lot of attention. So now I'm going to jump into physics. And the last part of this will motivate a lot of what follows. And in physics, there's one problem that I think, so Abhishek sent me some lecture notes that you were supposed to look at. But the most classic problem that's a rare event in physics is reaction rates. Okay, so you have a system. You have some system, some physical system, which is sitting in a metastable state, and you're interested in knowing what's the rate that this process happens. For example, this could be a chemical reaction happening, but it could be many other things. And for the equilibrium problem, this was solved by Kramer's way back when, and generalized by a James Langer to more than high dimensional problems. And one of the things that you should be able to do at the end of these talks is do this even for non-equilibrium problems. And in fact, if I have time, I'll show you how you do the calculation for the escape of an active particle over a barrier. And it turns out that the physics for this non-equilibrium problem is very, very different. Another problem, set of problems that, okay, there's a question. Okay, for the
Ion, you want to go ahead? There are also some questions in the chat box, I guess.
Yeah,
you want
okay.
to do it, I guess, at the end, or?
Well, I could do it now before I rush, because it was for the previous section. So, but if we look at, okay, I think that Sanjib addressed the A equals 0 and A equals 1 question. Again, if you're next to the end, then you have to, you have to account to finite really the next correction in order to do it in a careful way. Now, for an epidemic, I've been very, very vague. I haven't told you which model to use. For example, most SIR models that people use, at least I've talked to people who do it in Israel, there's no noise in them. And I think, at least talking with some experts, they're not even sure how to introduce noise in these things. But once you have a well-defined model, then you can ask, what's the probability of something to go extinct at some point of time, for example. Okay? Any other questions? Okay, if not, I'll move forward. So the other thing that, again, I'm not going to discuss, but there's been a lot of work on fluctuation theorems in recent years. And for example, if you take an isolated system, then you can show that the average over many, many experiments where you drive the system out of equilibrium by some process, for example, if you take a piston and you pull it, then under some assumptions, which are not very strong, you can show that the average over many, many histories of this process where you pull the piston with some specified protocol, you find out that the value of e to the minus the change in entropy in the system is equal to 1. And this specifically implies that there are cases where the entropy decreases, and you might want to ask, what's the probability of violating the second law? Okay, and of course this is a rare event, but nonetheless you might be interested in doing the calculation. Sorry, I'm being pedantic here. Okay, so the focus on of these talks will be somewhat different than what I've described so far, and what I'm going to discuss. Let me just see if I've skipped one of these. No. Okay, so the focus of these lectures will be on fluctuations, at least the motivation, fluctuations in macroscopic systems. Okay, so I'm going to spend a bit more time about than on other problems here. So what I'm going to do is consider a macroscopic system with n degrees of freedom. Okay, so some large thermodynamic-like quantity. Okay, and again, before jumping into a non-equilibrium system, in equilibrium, we can ask, given that the system is connected to a bath, what is the probability of observing an energy E in the system? Okay, so for the probability of to observe an energy, of course, if the choice of ensembles is crucial, and we know, and I've used it before, that the probability of observing an energy E is equal to the density of states at energy E. Because I'm connected to a bath, I have the Boltzmann factor e to the minus beta E, and I normalize by the partition function, and I can rewrite this as e to the minus beta E minus Ts divided by Z, which is equal to e to the minus the free energy as a function of energy divided by Z. Okay, now I can improve this a bit more. For example, Z is given by a sum over E of e to the minus beta F of E. And using what we said before, maybe somebody can answer me, what can I replace this whole sum by? Can somebody answer?
E to the power minus beta Fe star.
Perfect. E to the minus beta F E star, where E star is the energy at temperature T. So beta is 1 over T. Okay, so great. So with this, I can write that the probability of observing an energy E goes like e to the minus beta times the free energy at energy E minus the free energy at energy E star. Okay, so if you look at this, and a word of caution, if I have time today, I'll get to it, and if not, I might skip it altogether. That typically, in much of the literature, this is written in a slightly different way, but the gist of the idea is exactly the same. But what I want to stress is that the free energy F of E gives me the probability of observing a rare energy. Okay, so in that sense, from the point of view of StatMech, a free energy is a direct analog of a rate function or a large deviation function. And in fact, there's been a lot of work on putting on the two theories on the same footing. And indeed, they're the same essentially. Now, because F of E is extensive, I can write this in a slightly different way. I can write F of E is equal to N times some free energy density, where this guy is E over N. And then I can write that the probability of observing an energy density goes like e to the minus N times beta F of epsilon minus F of epsilon star. So going back to my previous definitions, this is my rate function or large deviation function. Okay, so knowing the probability of a large deviation in equilibrium gives us direct access to the free energy of the system. Okay, questions about this? So what I'm going to do is I'm going to take a macroscopic system and I'm going to break it into small boxes And the volume of each of these boxes, so the volume of each of these boxes will be some correlation length to the power d, the dimension of the system. So the dimension of each of these boxes is a correlation length, and we look at the generic case where the different segments, which are a correlation length from each other, don't talk with each other. Now the number of segments scales with n, the number of particles in the system. Okay? And what I want to do is I want to write down an equation for fluctuations in the energy. So suppose nobody told me about Boltzmann and all this stuff. I want to write down a dynamical equation for these fluctuations. So I write down some dynamical equation, and I'm going to argue for the general structure, not the details. So first of all, there's going to be a deterministic part. That pulls me to the average energy E star. Okay? And this guy, because we have n segments which are not talking to each other, this guy, and I'll be more careful with how I write it in a second, should scale like the number of degrees of freedom. And in addition, the system is chaotic and does crazy stuff, so there's a noise term in the system. Okay? Now, the noise term is a sum of the contributions from each of these segments. So how do you expect it to scale to leading order? Somebody?
Square root of n.
Square root of n, perfect. Okay, so I'm going to write this as square root of n times a noise term. Okay, because it's a sum of random terms. And okay, so what I want you to do is to notice that the deterministic part scales like n, and the noise squares like square root of n. So the noise is much, much smaller than the deterministic part. So in fact, to make this more in your face, in fact, write equation for epsilon, which is equal to E over n, and what you find out just by dividing by n is that you have the deterministic part plus a noise that scales as 1 over square root of the system size. So this is what I call weak noise. And it's very, very easy to understand why, if you look at an intensive, variable, that the noise will be small. Because if you want something very rare to happen, then all these different things have to conspire in a crazy way to generate it, and they're all fighting against each other. So generically, the noise is going to be a very, very small quantity when we look at a macroscopic system. And again, this is very, yes.
Sorry. So just to make sure I understand this, so you're thinking of let's say a box of gas, and you divide it into number of cells.
Yes.
So n is capital N is the what number of cells or the number of?
So it's not so important, but the important thing is that when I increase the system size, then the number of cells grows with n, linearly with n. But you could think about n as the number of cells.
Number of cells, and E is the energy in.
So E is the total. This is the total energy in the system.
Okay.
And E is the intensive variable. So I take the total energy and divide it by N. So again, it's, you know, just rewriting things. The important thing is that we have this deterministic part that scales like N. And the noise term, because it's a sum of random contributions, is it's a much smaller contribution than this deterministic guy. And this is more apparent if I look at the intensive variable. Then I have things that scale like 1, and then a very small noise that goes like 1 over square root of L. So the larger the system is, the more you have to fight against all these independent segments. And the noise becomes small.
Okay.
Okay? And in equilibrium, in equilibrium, the small noise, and we'll show it later, in equilibrium, this small noise, okay, we know actually, in equilibrium, the small noise leads to P of epsilon, which scales like e to the minus n times beta f of epsilon minus f of epsilon star. So what I want to argue, and I'll show later, that this n that is sitting here is directly related to the small noise. And that leads to this exponentially a small probability. And you can ask yourself, now, you can ask yourself, look at system out of equilibrium and ask probability for some event. For example, the probability of observing some density in the system, and I'm going to call this general event X, and the probability of this event, as I'll argue for many systems, behaves as e to the minus n times I of x, where this I of x, the rate function, replaces the free energy. Okay? So just to recap, the rate function in out of equilibrium systems, and hopefully we'll get to some examples, is a direct analog of the free energy. It's not as useful as the free energy, but maybe someday someone will make it as useful as the free energy. But it's a direct analog of a free energy in out of equilibrium systems. And as such, there's been tons of work on understanding this quantity out of equilibrium. So I'm going to end, because I'm just finishing my time, with two generic questions that were asked. And if I have time, I'll talk about them at the end. The first one is you take two baths with two densities, and you connect a simple channel. And people have looked so far mostly at the simplest case, where it's a diffusive gas in the channel. Okay? And one of the questions that you can ask is, what's the probability of observing some crazy density profile inside the system? So for equilibrium, that's an easy question, which is it's just given by the free energy of the system. And when I get to it, which if I get to it, I'll explain how you get it directly, but it's a very simple question. But you might ask, what happens when row left is larger than row right? And one of the most interesting things that people discovered, which in some sense was known already from early works by Spahn, but was quantified in a beautiful way, is that in contrast to equilibrium systems, where each block inside the system is, and again, all these words, if I get to it, I'll clarify, each block acts as an independent entity, which is decoupled from the rest of the system, meaning that the probability of observing this density profile is a product of the probability of observing this value here times this value here times this value here, etc., etc., etc. People found out that once you drive the system with a current, then this system becomes the probability distribution becomes non-local. So it requires a much, much more complicated structure, which I think is fair to say people still don't understand. Another class of question that people have looked at, which turns out to be even interesting in equilibrium, you take a channel connected to two baths, and these baths might be of equal density or different, and you might ask, what's the probability of observing a current J flowing inside the system? So that's a large deviation quantity. And there's been a lot of work on looking at these probability distributions. And one of the things that I find more interesting about these probability distributions, which also holds true for density distributions that I've described above, is that they turn out even in the simplest, the simplest diffusive gases which are out of equilibrium, they turn out to be singular. And I'll explain what I mean by that later in the talks, meaning, I'll just give a hint, meaning in the context of a density, if you look at the probability of this profile, but you look at the probability of a profile that's very, very close to it, you change it continuously, then the rate function changes. The rate function between these two configurations changes in a singular way, even for a silly, simple gas. So the structure of the probability, what this tells us is that the structure of probability distributions out of equilibrium, even in very, very simple systems, can be very, very complicated, and we're still trying to understand these things. So what I'm going to do in the rest of the talks, I'm going to start the talk tomorrow by giving a list of some references that you could get to at the end of the talk, review papers, etc. And then I'm going to develop a host of tools that's, I think it's completely standard now and being used routinely in any literature that you look. And I'm going to teach you how to calculate probability distributions for small noise problems. And we're going to do both equilibrium problems and non-equilibrium problems and contrast how different they are from each other. And time reversal symmetry and its breaking will play an important role in everything that follows. So I'm happy to take some more questions. I think I'm over time, right?
Yeah, okay, thank you, Yariv. I think there's some questions in the chat box.
Okay, so epsilon, yes. So again, just to define epsilon in a coherent way, epsilon is just the intensive energy. I take the total energy in the system and divide it by the number of cells in the system. So it's telling me something about all the energy in the system. And for the non-equilibrium kinetic rate problem, well, the standard problem, the standard books are Van Kampen and Gardiner, and hopefully by the end of the talks, you'll know how to do it using the methods I teach. And I think actually the lecture notes that Abhishek sent me has the standard derivation there. Abhishek can concur or refute.
Yeah, I think Sanjib, I mean, your notes, does it have the? I think it has some statement.
Yeah, I think it has towards the end of the.
Towards the end, right? Yeah.
End, I think probably. Like
yeah. So for the, I mean, so there are some notes uploaded in the website, so which has some of these discussions on large deviations in.
Okay, but again, hopefully even if I don't get to doing it explicitly, you'll be able to do it alone at the end of these talks.
Okay, no questions.
Yeah, maybe I'll ask one question. So, like in the cases where the tail like decays not exponentially but say in power law fashion, are those cases like interesting?
They're interesting. They're not covered by what I described in these talks. Okay. So there's methods of describing these things. They're not covered by what I do in these talks.
I just had a comment on this. So this question about this modeling COVID. So I guess the SIR model, of course, is deterministic, but I mean, especially at early times when the numbers are small, then I guess one has to write the stochastic dynamics, right? And then in this case, this really becomes important to.
Yes, and I've talked with the COVID. I tried to talk up some professionals, and the truth, they told me that they're not sure how to insert noise. You know, a physicist would put some multiplicative noise that goes to 0, and you would guess a square root of the density or something like that. But he told me that they think that it's more complicated and they're not sure what to do. So I'm not sure. If you ask a physicist, he'll probably solve it in a second. But sorry, I'm not trashing physicists, but you know, I don't buy my glasses. I told this to people in my group. I don't buy my glasses from the optics people in the Technion. I go to professionals. So they're not sure about how to put in the noise, if it's in the coefficients, the deterministic coefficients, or is it an additive noise with multiplicative noise?
Yeah, but you know, if I just think of like, say, I'm thinking, I mean, at a completely microscopic level, it's like if individuals are coming in contact and then with some probability you get infected. And so at that level, if I just think, then it's a completely stochastic process, right?
Yeah, then the physicists can work with it, but they're claiming that it's more complicated than that.
Is it okay?
I don't know. Look.
I thought the agent-based simulations are kind of like that, isn't it?
So if you talk with many people doing these modelings, that's exactly what you're doing is what they do. If you talk to somebody who's modeled viruses as a profession, from what I understand, again, take this with a big grain of salt because it's based on phone call conversations. He was discouraging me from getting into it.
Okay.
But maybe he was trying to get me off the turf or something. I don't know.
Okay.
So are there any other questions? So yeah, so I don't see any other questions. So maybe we again meet tomorrow.
Yeah, okay. And if you think about questions before the talk tomorrow, I'll address them. Before we move forward, the word of caution that will become more technical at the end as we move forward on very simple problems, but more technical. So it's good if you understand.
Yes. So one comment, Yariv. So is it possible to send the notes today so that we can put it so that the students can look at it before going to the next class?
I can do that.
Okay. Yeah. Thanks.
Okay, great.
Okay. Yeah. So yeah.
Okay,
see you
bye.
tomorrow.
Yeah. Thanks.
Bye. Yeah. Thanks.
Bye-bye.